It's a real pleasure. Okay. It's a real pleasure to be here, giving a talk about what I love most, research, not about administration, not about this and that, but a problem that has really occupied me for many, many years. Probably it has its roots. It does have its roots when I was a professor at the University of Athens. So, what is an inverse problem? Actually, when the title went out, few people asked me that, what is an inverse problem? So I thought that most of them would go to the web and see what places like Wikipedia say. And actually, it's a pretty good lemma in Wikipedia. I liked it, so I copied it. It's a process from the results of that a cause of a physical event produces, we try to infer about the mechanism and the arrangement of the sources that produce this effect. This can be electromagnetic radiation, gravity waves, you name it. It actually goes on and says that it has wide applications everywhere, and basically lists every domain of science and engineering, if you look there. So it's pretty clear that it's a very, very important problem. I have to say, in most curricula at universities, is not taught as such. These fields, I'm not aware actually, except in specialized graduate courses, that this broad scientific problem is not brought in a unifying theme, teaching our students how to approach a wide variety of problems in a unified way. Interesting observation. It's a 20th century problem, although the first probably important application of it was the discovery of the planet Pluto. Now, I understand it's no longer a planet. And by the disturbance of orbits of other planets, they inferred there was a planet. That's an inverse problem. They inferred something is causing disturbance on the orbits of other planets, and there was an extra planet. This is the way actually that exoplanets are detected these days. In other words, planets in other stars, not our solar system, exoplanets are discovered the same way. This pioneering work was done by mathematicians initially. Hermann Weyl, very important work in his work about describing the asymptotic behavior of the Laplace-Reytrami operator, as it's called in mathematics, which is basically the inverse problem. Out of that work, a nice story is that he conjectured that one could find the shape and of a drum by hearing the noise. It's a good way to visualize and yes, one said he can infer the physical parameters of a drum by recording. That time recording was not known. The noise produced by the drum. 6 years later, Johann Radon laid out the mathematics, which is very modern actually, of tomography, which is used now in everywhere. If you go to any clinic, that's basically what they're using. So, with this short introduction of what really a tomographic problem is, so the. I'll try to say a few things about how we approach the problem. We claim it's a novel approach to solving the inverse problem. It starts with, actually, when we started solving it, we didn't realize how broad the method was. I started doing this with my colleague, and we have been working ever since on this problem, Stathis Styliaris, professor now at the University of Athens. We did it in Athens, so we called it the Athens Model Independent Analysis Scheme. As you see, we didn't realize it had such a broad implications, but several years later, we realized that we were solving a very difficult inverse problem, a quantum inverse problem, while it had very, very broad applications, both in quantum and classical domain. And most recently, we have focused on the classical problem, which has wide social implications, medical tomography. So that's what I will try to say. Let me, underlying all this is this Athens Model Independent Analysis Scheme. If we know what we know today, probably we would have called it something else. Because it's not an analysis scheme. It is actually, but it's really has some broader implications than an analysis. So initially, as I said, it was developed. At that time, I was heavily involved in physics in addressing a very important problem, still is open, on the shape of the proton. The shape of the proton, most people immediately would say it's spherical. It is not. Actually, it's proven now that is deformed. The proton is not spherical, is deformed. How much and exactly, it's rather difficult to quantify. But the data at that time were very ambiguous, and the same data interpreted with various very complicated theories were giving diverging results. So at a workshop at MIT in 2004, followed by a second one in Athens in 2006, I made the statement that I will not take more data unless I learn how to analyze it. I thought it was easy. It took a long time. And at the end, we developed this method, which makes a very, very strong statement that it can produce totally unbiased results. I underline the totally, with maximum precision. This is, it sounds like a hubris. It's just, this is really very strong. Totally unbiased, maximum precision, that's heavy words. Okay, the method is so powerful because it relies on very simple hypothesis. Only one hypothesis is the so-called ergodic hypothesis in physics, which in this particular, I won't go into the ergodic discussion, that any parameter of a model or a theory can assume any possible value allowed by the model's underlying deep assumptions. Cannot violate rules of physics that we believe so much, like unitarity, causality, or basic things like that. Otherwise, anything goes. Any can assume any parameter that you may want. And the probability of this solution representing reality is solely determined by the data. Actually, epistemologically, that's everybody say, oh yes, we believe that, yes. But how do we apply it in solving the problems? So it looks like I said nothing so far except trivial truths that every scientist believes, and so it's very economical assumption, because if you base your assumptions so solidly on so broad principles, it's a good beginning. It's a good beginning, a hard way forward. Okay, how do you make analysis out of this? So the let's say a few words, and then I'll give you an example, because even the words will sound vague. So we assume that all possible solutions are valid, given that all measurements have uncertainty. There is no measurement that's of zero uncertainty, as we all know. That means that all possible solutions that do not violate cardinal principles are allowed. Okay, good. And so when we compare them with the data, we have to decide how good this solution is. So here we have a first choice. We have to assign a probability that this assumption of parameters of the model, these parameters of the model could be, for example, the parameters of the standard model of the universe, or it can be anything. It's a parameters of a model. Choose them randomly, and I'll tell you how probable that solution is, depending on the data. So we need a goodness criterion to weigh that probability. Here you have to make a choice now. For example, you can choose the chi-square as a goodness criteria. You don't have to. You can, I'll show, actually we use other goodness criteria, but here you have a choice. So there you introduce a bias, but you can choose any other goodness criterion to do it. And as you know, in just about any field I work, very few will question whether the chi-square is the source of your problems. Okay, so after you do that, keep throwing the dice, randomly get the parameters of the model going, and then you, if you gather enough solutions, so it's big data now, typically we do it for a few million times, you have an ensemble of solutions. And ensemble, it's meant in colloquial terms. We have a collection of solutions. Also, we mean it in the statistical mechanics sense of the word. So we construct micro, canonical, and grand canonical ensembles out of these solutions. Okay, now we're on solid ground, because now I have statistical mechanics, all the work done to analyze my ensembles. And I show you that I can construct out of these assumptions probability distribution functions. And that's the maximum you can possibly get out of the problem. So that has the maximum information, and that's the claim. So let's try to make an algorithm out of it. So we choose, we have a theory, a model, who has n free parameters. This is like capital A. And by choosing values, these are the little a's, choosing specific values for this set of parameters, I have a solution. Throw the dice, and I have a solution. I have that solution. I compare it to my data using a goodness criterion, let's say chi-square, and I assign a probability, and I assign a Boltzmann, in this case, type probability, and I say this is probable so much. So there are other goodness criteria, and we can have a whole seminar on goodness criteria, and we used in our work so far chi-square and psi-square. Psi-square is the chi-square is, you know, it assumes normal statistics, but if your data are sparse, and this is often the case, it's a bad criterion. You have to use Poisson statistics, which leads to the equivalent of chi-square, which is called psi-square, where it's the statistics are sparse. So we know how to do it. So let's understand by applying this to a law that we all like. It's very simple, but also very, very important, given that it's the basis of harmonic analysis. Hooke's law. Okay, you hang a mass from the spring, and the law says that the force is basically proportional to the displacement. Okay, so let's see how we can understand AMIAS with this. Well, we can take this, generate pseudo data, so we know exactly what to expect. This is a problem with two free parameters, A0 and A1. A1 being the spring constant, A0 being the offset. And I chose A0 to be 7, A1 that, with a given uncertainty. I can generate pseudo data, and so I know exactly what to expect at the end. So let's see what we can do. We can analyze this data. This is the generator. As you know, for a linear problem, there is an analytical solution to the problem. So the analytical solution is what you see. And I can use the garden variety programs that we all use, let's say Minuit, the Sun package, or GNU-plot, or take your favorite, and they all give the same answer, okay, as you expect. Okay, let's try to solve this with AMIAS. The assignment of probabilities now, it's issue. I throw my dice randomly. Actually, once I had a video showing the dice being thrown. And if I give the known solution, I'll get, of course, probability 1. Take the last, which is the red curve. Oh, I'm not seeing the same one. Why? Oh. Okay, so if I go to the red curve, and this is what the random variety says, this is solution. What is the probability of it being true? Well, it's 10 to the minus 53. But it's a finite probability. Some others have probabilities at 0.05, which is not so forbidden of being reality. So all of them, each one of these solutions is a point in my ensemble. So let's skip that one. And so let's make a histogram of the population of the ensemble. Well, here I have the one of these parameters. It's started with, we know it's 7, the generator, 0, 14, okay. And since I'm using the ergodic hypothesis, the histogram should be flat. All, if I'm true to that any solution is allowed, my histogram of all points there should be a flat distribution. Okay, we can start now cutting in. Say, suppose I need a probability of this being true less than 10 to the minus 20, or UPUI, or 10 to the minus 3. It's up to you. That will be a cut in probability, or a cut in chi-square, since chi-square was my criterion here. So if I say cut less than 950, well, I get this parabola. If I say less than 750, I get on and on and on. And you see that I get at the end the solution with a given probability. So this is a micro-canonical ensemble, as you know, as we narrow here the probability has the equivalent in a Boltzmann gas of the temperature. So this is the probability that I get. So let's keep the bottom chi-square plus 1, basically, as we would like to do. We can draw the curve around it. We can measure the width. And I can do this for the A0 and A1 parameters. And again, can put them in my table. So this is AMIAS microcanonical and GWIS, as expected. You get the same answer. Okay. Instead of projecting best solutions, which is the microcanonical ensemble, it's better to weigh each solution by its probability of being true. Don't throw anything out, just weigh them and make a new histogram. And let's go back to our histogram. So this is the flat distribution. Let's weigh them, and you get out the probability distribution function of the solutions that are suitable of being true. And you see, for several orders of magnitude, as it should, it obeys the statistics perfectly. I can get out of this the central value or the peak value, or now I'm simplifying, but just to put them in the table, because the best solution is the probability distribution function, is not a moment of it or a central value, but for the table, I do that. And I do this for A1, and I put it in my table, and yes, we get again the same answer. Okay, it looks like a lot of work to find something you can do analytically. It's a validation, and it's a good way to explain the method. For a nonlinear problem, already the advantages of AMIAS begin to show. This is a simple nonlinear problem. Okay, we get the solution, but I won't have, otherwise I would not go to the inverse problems. If I start explaining issues like that, I will make one point. If you look at Minuit versus AMIAS, and Minuit is a very sophisticated program, look at this. For certain parameters, the linearization done in typical chi-square minimization, as fancy as Minuit, it's this type of topology. In other words, it linearizes at the lowest value fine, it linearizes and gets absolutely zero. So out of the phase space of solutions, by finding the minimum and linearizing the bottom of the parabola, that's what is an answer you get. Way off in terms of evaluating the uncertainty, because this is a highly nonlinear problem. So linearizing a highly nonlinear problem is exactly what you expect, but this is what is being done. Most of the results you see in the literature are based on such analysis. So what is so different with AMIAS? It has several advantages. It's very powerful because of its minimal assumptions. We don't search for chi-square minimum, as you see. There was no search. So you avoid this linearization. You avoid being trapped in minima, etc. There is no minimization search. As you have seen, it's statistical. So it's also very stable numerically. Taking numerical derivatives, as we all know, especially with sparse statistics, with big errors, it puts severe restrictions. So because of that, there is no limitation to the number of parameters of the model. You can have 5, 50, or 500. It's stable, well, except the power bill it gets very expensive. But that's a different issue. Correlations among all parameters, as I have shown you, are taken into account, and prior knowledge, so you get to Bayesian questions, is trivially incorporated into this scheme. So it extracts the maximum information that the data allows. It's a very, very strong claim. They make it, and people don't like it, but nobody can argue why this is not true. The first reaction is, wait a minute. Okay, so let's summarize where we are. It's what I said. Basically, we make the ensemble and we tag it with a probability for each solution. Construct, I didn't tell you about, I told you about two ensembles. I don't have time to say about the grand canonical ensemble. It's a very interesting thing where chemical potentials come in and all that. But we'll stay with those two, and we get the results, which is probability distribution functions. And of course, out of that, you can get any moments you want, except in cases where it can be a function that has the PDF, not a symbol or Gaussian-like. We have cases where it can have 2 peaks, 3 peaks, etc., in complicated models, and this is the truth. Okay, so let's try to use it in complicated problems. I cannot see the time. This clock there is 1. Okay. So everything now relies on the model we're going to use that defines the problem we're going to solve. Okay. So if you have Fuchs law, I recommend that you use GNU plot. But if you have a very, very complicated, and this is we originally started using it for hadronic physics, addressing very, very complicated quantum problem with very complicated data. The data, the latest one I'm going to show you now, is from Germany, out of the crystal ball detector, a multi-million dollar experiment. Again, trying to measure the deformation of the product. Very complicated data. And the parameters that emerge out of it in this scheme are infinite. It's a multiple expansion, and you're looking for the dominant multiples. But as you know, with multiples, you have to truncate at a given level. No need to truncate here. So we present 50 or so multiples here, and some of the dominant ones have the information about deformation. This is from the publication. It's the same flow chart, except again, here is the model that matters. The model is the Chu-Goldberg-Low-Nabu model of the nuke of this reaction. And if you judge from the names, 3 of them have the Nobel Prize. It must be a pretty heavy theory, and it is very computationally demanding. It was done. We get the observables, and this is the forward model. So if we have the observables, I'm beginning to use now inverse problem language. We know how to go from the parameters to the results, and that's what you need. We build the observables, and you publish them. This was part of the thesis work of Marco, PhD from the Cyprus Institute. It's a major publication because it's the most precise now measurement on this electric quadrupole to dipole ratio, EMR is called. If it's 0, the nucleon will be spherical. There's no ambiguity here. It's definitely non-zero by several standard deviations. And here, the emphasis is on how many standard deviations. It's above 5, so it's a discovery, according to CERN. And many other measurements have been done before. Some of them are of our group in Athens or MIT. but this is the definitive answer now, based on these results. Another issue is that we managed through this to, again, with Marco, to test the so-called Fermi-Watson theorem, a theorem that was proposed by Fermi, very important in understanding data. It has to do with the phases of scattering amplitudes. And for the first time, we were able to validate it through a very complex analysis. More recently, work by theoreticians in Athens and Polish Academy of Sciences analyzed CERN data, looking for transition in QCD, where the transition is to go from the normal QCD state to live in. At high temperatures, you have a phase transition. It becomes a plasma, the so-called quark-gluon plasma, like atomic matter. If you give it enough energy, it becomes fluorescent. It's the atomic plasma. And that depends on critical exponents in the theory of phase transitions. And this is the results that emerged. This is a very recent publication that claims that CERN, through this experiment, has exceeded the critical value for transitioning to a quark-gluon plasma. Here, the important thing is that it's a very noisy experiment, noise, not instrumental noise from the competing reactions. The signal is estimated to be less than 1% of the reaction channel. Other reactions contaminate with similar products they detect. Very difficult experiment. We also convinced here the very well-known internationally Lattice QCD group led by Dean Alexandrou, with very heavy involvement of Theodore Leontiou from Frederick, to apply this to the data they produce. They call it data. They are simulations, really, but in their language, they talk about their data. We argued that they spend inordinate amount of computing time to get these data, but they analyze them in a very simplistic way, in my view. Eventually, we agreed that let's give it a try, and produce results that are superior to the standard practice in lattice gauge theory community. Dina and Leontiou proceeded, this was the beginning paper, to produce other papers using the same technique. Okay, I gave you some background where we used AMIAS. And then before all this work, as you see, this work is rather recent. Now AMIAS is well developed, well understood, very hard to apply. It takes this. People have to have the patience to learn. It's not like, let me get a GNU plotter, throw the data in, here comes the answer. Really, it takes more than that. So it is a big impediment. Also, considerable amount of computing time. It's a long story. I won't give you the background. At the same time, both studies, primarily studies, and me, to some degree, we were involved in medical physics. And the two things came together. And one day we said, hey, isn't this something we can apply to classical, to a medical physics inverse problem? At that time, we had to learn what the inverse problem was, really. And that we moved AMIAS to medical physics. So AMIAS shows, I said already, that the forward model, what is a forward model? It's nothing else that the model we had in the AMIAS algorithm we used all the time to generate the ensemble. That's the forward model in the jargon of inverse problems. You make the statistical ensembles. Hey, you don't need the backward solution anymore. It emerges only through the statistical physics of the forward problem. So why don't we try that? And this could not be done without HPC. And actually, looking in the literature, clearly, these guys had the right idea. This is for Neumann. He was fascinated by, and as probably know, or you may agree or disagree with me, is one of the fathers of, if not the father of high performance computing. He was behind the Los Alamos project, and his wife, actually very notable scientist, became the first director of the, would have been an HPC facility then, which is of course ridiculously slow, but they were both fascinated with the inverse problem. And from, maybe I'm imagining, but if you look at their work, clearly they wanted to attack it with computational resources. How they were so fascinated that they named their dog Inverse. So maybe that was the problem. Inverse problem was the dog, but they were fascinated by that. So inverse problems are everywhere, as Wikipedia says these days. I showed you some results. So let me focus on the last one we're considering. Here I have activity at the Cyprus Institute with that, and see how it does. Well, medical imaging is everywhere these days, and actually, this is a double-headed gamma camera, which actually we used such a device for some of the data I will show you. And the data such devices produce are summarized in something that the data is used for the side of them. And I'll explain briefly how it's taken. And starting from this data, you go from the sinogram, usually the way it was done historically, you go from the sinogram to the radon theory, 1917, which, by the way, remained dormant until the 70s and 80s, because without computers, let alone high-performance computers, you couldn't do anything. So the computer enabled tomography, and you get this stuff. So this is the inverse going backwards from the data to the image. Of course, the direct forward go from the source of the that produces the radiation that generates the sinogram. That's how you get the data. So you don't need actually to understand that to analyze the data. The data with the random transform, if you have this data, somebody gives you the data, you can inverse it, and you have no idea if this was a human or a bicycle or the X-ray of my briefcase. No need to know the forward. Most of the technology used today is agnostic about the forward. So you see now already the big difference between what we're doing, because not only we are not agnostic, it's necessary we know the forward solution because we don't have a backward solution. The radon is just exemplifies this problem. Of course, there are other ways these days. Some of you are real experts here that skip Mr. Radon and then use neural networks to do the job, and they're exceedingly successful results in a number of modalities. Where actually for skin cancer now neural nets are doing better than individual doctors. they're competing with an assembly of doctors, whatever that means. So it's really, and with I'm not going to go here. I mean, I see Haris Chrysostomos here, who has been working on this problem. We're working together in the overall problem, and of course, Konstantinos and others experts in this can tell you the story much better than I can. Let me, this is part of what Anna is doing for her thesis. I just explain how the data are obtained very briefly. Basically, what what she does, she takes images of with an infrared camera, let's say of a column of this a column of watts actually with a heat resistor inside. So outside, if you take the thermal pictures, you get something like that. If you take a slice of it, and you take many pictures, and you rotate it. So these are the 72 rotations in this case that she took. And so each picture represents, you take a slice, and you take the slice, it looks like it's somewhere here. So you have 72 slices, and this is the synogram. That's why the data are there. It's a synopsis of the tomographic take on the data. In this time frame, I cannot explain much about it, but it looks this funny sinograms. Is this data? Yes, it's very complicated data, which are synopsized in that way. This is again a thermal image from the work that Anna is doing. You generate the sinogram, you push it through the standard. These are the state art of the art of tomography today. And either you use the filter projection or the maximum likelihood expectation maximization algorithms. And this is what you get. Well, you say it doesn't look at all. Look what the thing look like. The two resistors are there, and this is actually considered to be the Rolls Royce of the algorithms, and it gives nothing. Why? It's a notorious problem in inverse problems. Going forward, it's as a mathematician say, it's an into mapping, so it's 1 to 1. Going backwards, it's onto. You can go from 1 to many. And thermal tomography, which we claim we had the first applications, has been promised for 50 years. It goes nowhere because it's an excellent example of that. If you give the program agnostic as it is, to tell you where the sources are, generally they will put them on the surface. That's where what you see. You take a thermal camera of the patient, you want to use it for medical, you see the variations of the temperature of the skin, say, construct with the inverse problem, what generally that, they will say, oh, the skin is hot. It doesn't go any better. So it's what you expect, and that's how it works. Well, here we go to AMIAS, where it's not agnostic, and it gives the it's a very good representation of what it is. And of course, all three give equivalent results. Exactly with the data compared to the original data, just as good, all three. So you couldn't tell which it is by chi-square. If you are agnostic, you have to inject some knowledge about forward motion. Okay. This gave rise to RISE. RISE is a reconstructed image from simulations ensemble. And this is the algorithm. It's better to explain it this way. So this is what is the state of the art. Okay, so you go from the sinogram to the image. You do it with an artificial network, with neural nets, or you do it the old-fashioned way, as Mr. Radon did, or with fancy iterative methods like MLM. That's what it is today. Okay, RISE goes beyond it. So we need a physical representation. We need a model. Otherwise we get nowhere. Okay, this is the biggest headache of all. Because tomography, you go to a doctor and say, give me your forward model. You look at your model, it says you are at the wrong department, the psychiatrist is forward, down, forward, what is this? You need that. You need physical representation. You have physical representation where on the familiar curve, AMIAS get physical representation. Actually, you can get an image out. I showed you. Yeah. This is not good enough, though, because now you have idealized the world with the physical representation. And this is not like the standard theory of particle physics. It has a lot of if, and therefore this is an idealized result. And as being a scientist, not a theologist, you must rely and come back to data. So you have to go one layer down to go back to the data and reconcile all that. That's what RISE is all about. Okay, we used it in emission tomography. That in this case is direct single photon emission tomography, widely used. Like the camera I told you, this is what results. Actually, these results are from an experimental high resolution camera. We used a phantom. Phantom is jumping, it's an experimental setup, you know the answer, with 3 radioactive rods embedded in a radioactive liquid. And so this is what it is. It's hardware, and when you take a tomographic image, you'll find 3. This is what AMIAS or RISE gives. Actually, this is the idealized result. These are the MLN and the algebraic reconstruction, another method, and you see they're lost. We published the first ever thermal tomography. As I showed you, we could get answers. This is a fundamental picture here. In gel that has the same properties as human tissue, but 3 resistors. This experiment, the temperature was high. So it's not good for medical physics, but it's a proof of principle. And you see, we were able to reconstruct the fund. These we published, and I believe it's the first publication on claiming that there is validation. The competing methods, as you see, do very poorly. Time is running out. There is global demand for more accurate medical imaging. For cancer, for example, your doctor is very happy. He can detect a lesion or something that is smaller than 3 centimeters. That's why it's really below 1 is beyond the electrical really big. So the smaller you get it, and where it is important, these are real data. This is from Limassol. This is part of the work of the thesis of Christos Nemesiou here. This is from the German Oncological Center, Limassol. This is what the machine gives. And we analyzed the data. That's part of his thesis. And you see how more precise, there is no ambiguity. There is nothing going on here where the doctor might have suspected that I spread it out. And if you are trying to do radiation to this poor fellow, you have to know exactly where to create it, which is the definition. So this may be a life, let's say, probably. So higher resolution, higher contrast, early diagnostics. This is from a different modality. This is from the medical center in Athens. This is again out of the machine. This is somebody who has Parkinson's disease. This is shown by the lack of activity in this lobe. And this is state-of-the-art scanner. The machine I showed you also in the picture. And it's a Parkinson's disease. And to see if the pharmaceuticals are working, you need to map how this is reacting. So you need the highest possible definition. This is what our method gives. So these are real data now, okay? And you see it's accurate diagnosis and advanced monitoring. I'll conclude with this. This is published results. It's from an experimental high-resolution camera, not available in hospitals. It's a mouse. And you can see the resolution and the clarity we get clearly fraction of a centimeter. This dead mouse has been injected with all sorts of diseases, and we found all of them. So both in hardware, of course, here you cannot get this clarity with a hospital camera, but the ability of RISE/AMIAS is evident. Let me conclude. Okay. I hope I convinced you that AMIAS is a powerful method for solving inverse problems and other problems. The method has been examined extensively in nuclear high energy and medical physics. It is truly model independent, but you need to have a model. Extracts the maximum information, has no linearization, incorporates correlations to all orders, allows the incorporation, I didn't give you an examples of prior knowledge that you can inject, is stable and robust for reasons I explained. So what's the catch? The catch, of course, is very, very expensive computationally. Askanda, she's begging all day for more and more computer time. The RISE, which is tailored to medical imaging, tomography, has been extensively examined at the lab, has been successfully applied, but it's one case here, one case there. We cannot go forward unless we have medical validation. That means that a team of doctors takes, I don't know, 100 cases, find false positives, false negatives, does statistics, compares them with their standard protocols, etc. It's a very, very cumbersome and time-consuming process. Needs optimization, so it runs faster. It allows fusion of images. I didn't go into that, which is the best way to incorporate prior knowledge. In other words, you can fuse CT image into a PET image at the level of analysis, not as they do it now, basically overlaying one over the other. And I didn't say anything, just hinted that AI, and we're discussing this within the team, and Harris and Stathis are really at this moment looking into it, incorporating into the pipeline elements of AI, and not the whole thing, which we believe is the right way to go. So I will conclude and thank you, and I want to acknowledge all these colleagues of mine whose work was shown. Here it's worth pointing out the last four have been PhD or current PhD at the PhD program of the Castor C. Thank you very much.